I welcome one and all present here on 6th session of day 3 of ATAL sponsored 1 week FDP on unlocking the future, exploring the transformative power of 5G and beyond from 4th December to 9th December 2023, organized by Electronics Engineering Department, Rajki Engineering College, Sonbhadra. It gives me immense pleasure to introduce and welcome our eminent speaker, Dr. Sanjeev Sharma sir, IIT VHU. Now I would like to invite Deepak Sigroha sir, kindly welcome him with a plant. Sanjeev sir, please. Thank you so much, sir. Dr. Sharma is working as an assistant professor in the Department of Electronics Engineering at IIT VHU Varanasi. He has completed PhD from IIT Indore in 2018. He had worked in Department of Electrical and Computer System Engineering at Monash University, Australia, as a postdoc fellow. He has published more than 30 research papers in the Journal of Repute of and conferences. Most of his publication in IEEE journals and conferences. He has chaired number of conferences and delivered invited talk in conferences, workshops, symposium, and short-term courses. His research interest includes developing physical layer techniques for next generation wireless communication system and application of deep learning to design of wireless communication systems. During his PhD thesis, he worked on the spare signal processing technique for wireless communication. Sir, we are very glad to hear you. Thank you so much for accepting our invitation. You are also you are requested to kindly start your session with the title 5G and Beyond Wireless Technologies. Sir, please.
Yeah, thanks, Dr. Verma. So, this talk we will generally discuss what is the possible technology for 5G and beyond people are looking. Okay. So, that is not guaranteed that every technology is going to implement, but people are looking some new way to implement the communication system or design the communication system. And so, we will go some recent technology that people are exploring for 5G and beyond. Okay. So, first we will look what is the motivation 5G and beyond. Earlier speaker already talked about motivation about 5G and beyond. Okay, we just briefly go over it. Why people are why every 10 years we are looking next generation communication technology, like for example 2G, 3G, 4G, then 5G, then people are already start talking about 6G. Okay, so if you look the gap every 10 years we are getting new technology and people we just call it next generation. So, first 1G, 2G, 3G and 4G so on. Okay. So, we will look some motivation brief, then key wireless technologies we will talk in this presentation, mainly this non-orthogonal multiple access techniques, MIMO, multiple input, multiple output, then intelligent reflecting surface assisted wireless system design, then OTFS, as earlier speaker already talked about it, orthogonal time frequency space modulation, and currently people are also talking about AI ML based wireless system design. Okay. So, then some other technologies, then future research direction we will look, and then we conclude the talk. So, if you look the 1G, it is deployed around mid 1980s and it's mainly used for voice services. Then 2G is 90s voice services, then 3G in 2000 primarily for voice services, then 4G is deploying for primarily data services. Okay. Then 5G mainly people are developing for or deploying for IoT services, and then if you look every 10 years we have a new wireless technology that we calling 1G, 2G or 5G. Then so every generation 1G to 5G we are getting higher data rates. Okay. So, higher data rate is not only the motivation, every technology have new features that will serve the our multiple purpose that we are coming new every days we are getting new applications. New applications are coming from various sectors. either healthcare, agriculture, or industry, or some academia or some other backgrounds. Okay, because our daily basis demands are changing, our scopes are changing time to time. So, as time progressing, we are getting new applications, then current technology is not able to fulfill those demands. Okay. To fulfill those demands, we have something new. Okay. So, we have something new means we have to do something new, so that we can fulfill those criterias. Okay. So, those criterias or the demand from the various sectors are pushing us to develop the new system, wireless communication systems. So, we then we calling that 1G, 2G or 4G or so on. Okay. People already start talking about 6G in uh, what happened? I think this.
Sir, just go to next slide, sir. With this, now side में आ रहा है, ये zoom कर, तो zoom के लिए side में वो आ रहा था indicator, और zoom कर दिया आपने,
नहीं कम की. We go. Now we can go full screen. I think. Is this? Yeah. 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 So, every generation wireless technology have higher data rates than new technology. For example, if you look the 3G, we use the CDMA technology, code division multiple access. Then 4G we are using, on 5G we are using OFDM. Okay, so CDMA, especially in this 3G channel, wireless channel is there between transmitter and receiver. So, channel is considered basically in the time domain. Here in 4G and 5G in the OFDM, channel we explore in the frequency domain. Okay. So, this is the kind of way to handling the channel. Okay. If you just think transmitter and receiver, between transmitter and receiver channel is there. Okay. Channel is not in our hand, channel depend on the surroundings. For example, if you have a rural area or the urban area, channels properties are different. Okay. So, we cannot modify the channel or manipulate the channel, channel depend on the surroundings, it is not in our hand. What is in our hand? Transmitter and receiver. So, we can tune the transmitter, we can also tune the receiver. Okay. Transmitter receiver we can design and change and manipulate according to our requirements. Okay. So, what is our requirement? That channel basically the between transmitter and receiver that depend on the surroundings. So, can we look the channel in a different angles? A different angle means different ways. Maybe I am looking the channel in time domain, he is looking channel in the frequency domain, then doing the processing at the transmitter and receiver, or designing the transmitter and receiver. Okay. So, maybe I will explore some properties of channel in the time domain, and he can also explore some different properties of channel in frequency domain. Okay. So, that is the idea behind 3G CDMA, channel used in the time domain. So, transmitter receiver design based on the time domain properties of the channel. Okay. Then people thought that, oh, the time domain channel properties are not good, can we look in the channel in frequency domain. Okay. Then OFDM, orthogonal frequency division multiple access, this LT we are using, channel is explored in the frequency domain. Okay. Then new some properties of channel explored in the frequency domain, and transmitter receiver are designed. Okay. Then we getting that better system design in the if we consider channel in frequency domain. So, that is a main motivation. So, basically new technology development meaning is that you are looking the existing things in the different ways. Okay. When you look the existing things in the different ways, maybe you can get better understanding of those things. Okay. Suppose you have this object, if you look just front, then maybe you have some information. If I just rotate it, or you have a all 3D view of this object, then maybe you have a different aspect of this object. Then you can well understand that object, and you can tune your system according to that. So exploring those properties of the channel, okay, or that that basically we are doing from 1G to 5G or beyond we will do. Okay. So this is some key performance indicator. If you look the 5G and LTE, so LTE I am just calling it 4G, and key performance indicator I am just looking here the latency, throughput and connections, and mobility and network architecture. So if you just look the latency we are looking the 5G 1 millisecond, and here LTE or 4G we are looking 30 to 50 milliseconds. So there is a gap, 30 to 50 times we have to improve the latency between 4G to 5G. Similarly, if you look the throughput we are looking 10 gigabit per second, but if you look the 100 Mbps, so there is a gap. Okay. So similarly here the density means number of users per area you can handle. Okay. Similarly mobility we can expecting like 500 kilometer per hour your network can support. Currently you can see that as a train is moving high speed, you cannot get good connectivity, so your call is going to disturb. Okay. So similarly the network architecture, so this inflexible meaning is that once your network is deployed, network means there is some hardware components or physical entities, they are just deployed, then they are fixed, but we are looking something flexible. Okay, but that we can modify according to our requirement time to time. Okay, so that is the flexibility we are looking. So if you can see this gap here, 30 to 50 times we have to improve this latency, 100 times we improve the throughput, then 100 times we have to increase the density, user density, then mobility and all those things. Okay. So this we okay, that is the idea, let we have to improve those things, but question is that how we will improve those things. Okay, that is the next question. If you have the problem, then we have to think what are the possible solutions. Okay. So possible solutions, improving these KPIs, key performance indicators, from going from 4G to 5G, we need to think differently. We need to think differently means we have to think system design in different direction point of view, not as the earlier people have already considered, so that this can be improved. Then if people thinking new directions, then we saying that new technology is developed for the system design or wireless system design. That is generally idea. Okay. So then if you just looking this 5G to 6G, people already talking about 6G. So this is again a gap between 5G and 6G. Then you can see some again a performance we have to improve if we are going from 5G wireless network to 6G. Okay, even currently there is nothing is fixed for the 6G, but people just guessing the key performance indicators that 6G should fulfill those things, but nothing is fixed. Okay, till now. Okay, so some new things is coming in this. There's and this processing delay and that positioning accuracy, energy efficiency, especially we are looking. Energy efficiency, why we are looking energy efficiency? Energy efficiency means if you just have the system consumes certain amount of power to transfer the data or receive the data or both. Okay. So if you have like you just think mobile phones, everyone has that 1 or 2 mobile phones. Okay. Even we are consuming very less power. Just think battery. Okay, but if you just total you can consider like how many mobile devices, just only mobile devices you have. Okay, then think about how much total power we are consuming. Okay, that is the in our pocket. Okay, if you just think at the power generation house, okay, where we have a lot of like very less efficiency from that power generation to your home. Okay, so think about that, how much power we are generating for that mobile devices only at that the end. Okay. So this energy efficiency and spectral efficiency we are focusing highly in the 6G wireless network design. Okay. So that is some use cases. So I am not going on these details. As I pointed out, 5G is mainly coming for IoT applications. Okay. So this high speed connectivity and on demand video streaming, all those things. Then driving force of 5G is that society, environment, and economy, and users, operators, agriculture, etc. Okay. So that is a question we are looking. As I pointed out, throughput means you can just think about data rate kind of thing. So throughput, I am just looking the bits per second per square kilometer. Okay, that is the area you can think. So throughput I can quantify in the cell density, available bandwidth, and spectral efficiency. Okay, if you remember that capacity formula, Shannon capacity formula. So data rate is generally B log 1 plus SNR. Okay, so so if B is in the front of log, so is linearly proportional, data rate is linearly proportional to bandwidth. Okay, so if you increase the bandwidth, data rate we can enhance. Okay, then another thing is the cell density. Cell density means like particular area you can divide into smaller parts, then each smaller part have a separate base station. Okay, so then whatever frequency resources you have here in the one cell, we can reuse those resources into another cell. So that is called a frequency reuse, okay, or resource reuse from one cell to another cell. Okay, then question is that if you have a like a smaller cells, you can use more, frequency reuse will be high. Okay, so what that meaning is that available frequency spectrum you can utilize multiple times. Okay, so that means cell density will increase the throughput also, because frequency reuse is going to increase. Okay, then we have a spectral efficiency. Spectral efficiency is another factor. Spectral efficiency you can think in the modulation order, maybe you remember in the digital communication. Okay, BPSK, QPSK, 8 QAM, 16 QAM. So as we order of modulation is increasing, that means number of bits per symbol is going to increase. Okay, so it's meaning that more bits we can transmit per second, you can think that. So if you transmit more bits per second, we can increase the data rate also. For example, BPSK have a like data rate is 1 kbps, then using the QPSK you can go for 2 kbps. Okay, so that means spectral efficiency means more number of bits per hertz we can transmit, so that spectral efficiency can increase. Okay, so spectral efficiency will increase, throughput will increase, then available bandwidth will increase, throughput will increase, then cell density will increase, throughput will also increase. So either one you can consider to increase the throughput, but some challenges are also there. If you increase the cell density, then what will happen? Cell density means a smaller cell size. Okay, just think about 100 meter size, for example. So you have to repeat the base station every 100 meter. Okay, or if you have a like every base station in every 1 kilometer, so just think in 1 kilometer you just one base station, or you have like 10 base stations. Okay, so that is good, cell density increase the throughput, but challenges are coming. Instead of installing one base station, you are installing 10 base stations. So you think how much cost we will increase, how much infrastructure we will add. Okay, so that is not practically also possible to reduce the cell density like beyond the particular level or threshold. Okay, so that is a challenge. Cell density will also increase the cost. Okay, so that is a main challenge. Another thing is that cell density will also increase the interference from the neighboring cells. Okay, so interference issue is also there. So we have to think signal processing in different directions, so that we can minimize the interference. So that is a challenge that related to the cell density. Another thing is that available bandwidth. So bandwidth, if you look sub 6 gigahertz, almost 6 gigahertz, people are saying bandwidth almost fully occupied. Then we are looking the new bands. Okay, we are going beyond 10 gigahertz. Okay, so even if you look the 5G mobile phones, that is a one band is reserved above 20 gigahertz. Okay, that is around 24 or 28 gigahertz. Okay, then some people thinking about around 70 gigahertz. Okay, so going to higher frequency, we have a more bandwidth available is there freely, no one is using that one. Okay, so that bandwidth we can explore for the communication. Okay, so but challenge is there, as we going higher frequency bands, then losses are high. Signal processing, we need different signal processing aspects as compared to the lower frequency. Why? Because there is signal propagation, signal is going from one point to another point, so there is a attenuation or some kind of losses are associated. Okay, so those losses are increasing. Okay, so if losses are increasing, then we have to think differently in the signal processing domain to design the reliable communication system. So that is a challenge is associated due to the higher losses. That's why people again this people initially thought we will go millimeter wave or the terahertz communication, but people now stop talking about terahertz communication, especially for 6G. Okay, yeah, they this coming around 10 gigahertz only. Okay, so that available bandwidth increase the throughput, but also increase the challenge in the signal processing point of view or higher losses. Then spectral efficiency, as I pointed out, higher order modulation we can use for the spectral efficiency. But question is that if you just think about the 8 QAM or 64 QAM, okay. So if you consider the average energy is constant, means average power or energy constant, then spacing among the symbols you can see that decreases. You just putting 8 points, okay. Then you are putting the 64 points. So if you keeping the constant power, then the distance between the constellation points is going to reduce. So that is the noise immunity is going to reduce. Okay, if points are closer, then they are easily going to overlap due to the noise. Okay, so noise immunity is going to reduce. Okay, its meaning is that if you want to higher spectral efficiency by using higher order modulation schemes, you have to have higher SNR, signal to noise ratio, at the receiver side. As when SNR is high, how we will achieve high SNR? By transmitting the higher transmitted power. So that will reduce the battery life. Okay, so that is another challenge. So this is good for enhancing the throughput, but is also a drawback that we need high SNR while decoding the signal. Okay, so certain drawbacks and advantage and disadvantage are associated with each technology. So we have some trade off where we can optimize both things. Okay. So coming slides we are going to discuss this massive MIMO. I am just also pointing out massive MIMO we can achieve the higher spectral efficiency. Massive MIMO means we can have multiple antenna at the transmitter and multiple antenna at the receiver. Okay. So what we can use MIMO technology in two ways. One way is that if you have, like for example, 4 antennas, I can transmit one symbol using all 4 antennas, then I will receive the signal. So what will have, I can create multiple paths between transmitter and receiver, so I can increase the diversity. Okay. So that is the one advantage of MIMO. Another advantage is that another way of using the MIMO is that if I have 4 antennas, I can transmit 4 different symbols at a time. Okay. So its meaning is that we are increasing the data rate, spectral efficiency we are increasing. So that is a multiplexing gain we can have. Okay. So diversity gain or multiplexing gain we can have using the massive MIMO in our system. Okay. Then higher order modulation scheme that can be also used to enhance the spectral efficiency. Then I am just going to highlight this one, non-orthogonal multiple access techniques, higher spectral efficiency. So how will increase the spectral efficiency using the non-orthogonal multiple access techniques, that I am just looking. Then this is the cell density. So cell density here you can see higher, here is lower. So increasing the cell density we can increase the throughput by reusing the resources more efficiently. Then I am just coming to a basic block diagram of the communication system. We have a source that is generating the bits, then modulator basically a block that maps incoming bits to the waveform. Then channel, we have wireless channel, then demodulator, and then we have a sync. So you can think this part is the transmitter and this part is the receiver, and between them is the wireless channel. So this is the transmitter and these are multiple receivers. So transmitter is sending the information to multiple receivers, that is called broadcasting channel or downlink channel. Why it is broadcasting? For example, FM radio stations, only one transmitter is there, multiple FM receivers we have, then it is called broadcasting or the downlink or transmitter to receiver. Then similarly multiple receivers are there and transmitter is there, they are simultaneously sending the data to the transmitter. Okay, that is called uplink receiver or multiple access channel. Which channel is the same, but multiple users trying to access that channel, that is why it is called multiple access channel, MAC channel or uplink channel. So this is the system design. System design, if you look the wireless system design, we want low complexity. Low complexity is definitely associated with the cost. Okay, if low complexity means low cost. If you design a system, that should have low complexity or low cost, so that people can purchase it. Okay. Then power consumption should also be very low. Okay. but trade off is there. Generally, if you see, if system complexity is less, means its performance generally going to degrade. Okay. So, that is a performance is going to degrade. So, there is a trade off between system simplicity and performance. Then another thing is, I already pointed out, between transmitter receiver we have a wireless channel, that is generally we called channel impulse response. Okay. So, channel impulse response property we have to exploit while designing the transmitter or receiver. So, here I am just introducing a multiple access technique. So, as I pointed out, here we need, this is a multiple receivers and transmitter, here multiple receivers and transmitter. So, receiver either receiving the information or either they are sending the information, we need to use the channel efficiently. Okay. For example, channel meaning is there, so you have some physical quantity. Okay. Physical quantity, suppose you are assigning the multiple users, then we have a limitations. For example, you have a 10 apples, you can assign maybe 1 apple to each 10 persons. Okay. So, you cannot accommodate like 11th user or something like that. Okay. So, how can we efficiently utilize those channels, available channels between transmitter and receiver, that we are going to look. Okay. That is called multiple access schemes. Multiple access scheme means between transmitter and receiver channels are there. So, how multiple users can access that system. So, first I am just looking the orthogonal multiple access scheme. So, orthogonal multiple access scheme, just looking conventional, these are the conventional multiple access scheme. One is the frequency division multiple access schemes. Frequency division multiple access schemes, if you look, you have a frequency resources. Frequency resources are partitioned into the different frequency bands. For example, this is the first band and this is the last band. Okay. For example, count here we have a 1, 2, 3, 4, 5, 6, 7 frequency bands. So, we can assign 7 users. User 1 is using this frequency band, user 2 is using this frequency band, last user is using this frequency bands. So, user, but if you look, the frequency bands are orthogonal to each other, because one user is using only one frequency band, there is no other users in this frequency band. So, separate frequency bands are assigned to the each user. So, this is called frequency division multiple access. Okay. And this is also orthogonal multiple access scheme. Why it is orthogonal? Because only one user is present at particular frequency band, but all the time user are communicating. So, all the time all the users are communicating, but using the different frequency bands. Then if you look the time division multiple access, time I have divided into slots. Okay. For example, you have a 1 second slot and 5 users. So, what you will do, 1 divided by 5.2 second slot you can assign first user, then next 0.2 second you can assign second user, and so on. Okay. So, frequency is common, all the frequency. For example, if you have a 10 megahertz bandwidth, you can assign all the users, but users are divided based on the time slot. Okay. Let this time slot one user will go, this time slot another user will go, and so on. So, time slots are orthogonal. Why they are orthogonal? Well, because only one user is present at this first time slot, and so on. So, this is called time division multiple access schemes. Okay. Then another one is the code division multiple access scheme, CDMA, where the time and frequency, all the users simultaneously communicating as all the time and frequency, but they have a different codes. Okay. This is the code 1, this code 2, this code 3, and code 4. Okay. So, 4 users can communicate if you have a 4 codes. Code have certain properties that they generally orthogonal. Okay. Orthogonal meaning is that, what is the orthogonality condition? If 2 signals are orthogonal, then they will multiply, then integrate means average. Okay. And particular time duration, then this is going to 0, that we can say that orthogonality condition. So, if you will code 1, if you multiply to code 2, then average is equal to 0. Okay. So, that is the, so again these all 3 schemes are OMA scheme, orthogonal multiple access schemes. Then OFDM, orthogonal frequency division multiple access schemes. So, you can have multiple users. Then this is also OMA scheme. Why it is OMA scheme? Just look that. As earlier Dr. Atul pointed out, you have a time and you have frequency. Okay. So, time we have divided into multiple slots. Okay. Then frequency you divided also into multiple subcarriers. So, these are generally called subcarriers. This is called slot. Okay. So if you have 4 users, then how will divide those resources? So time and frequency, then we can divide in the grids. You can see that first grid, so on. Okay, so you can think in matrix. Okay, then user 1 may be allocated this time slot and all these frequencies. User 2 can allocate this time slot and all the frequencies and so on. Okay, so this way, but you can see at particular grid only one user is present. So this is the orthogonal multiple access scheme. Okay. Similarly, another way to assign the multiple users in the FDM system is this one. You just assign all the time to all the users, but you assign different frequencies. Okay. Then another one is that way you can just scatter the resources among the users like in this way. Okay. Generally it is better. Why it is better? Because in this way you can see users spreading in more in time and frequency, so maybe they get better diversity. Okay. So these are 4 schemes are orthogonal multiple access schemes. Then this is a OFDM block diagram, so I am not going to detail, just giving the idea what is a OFDM. As I pointed out earlier, OFDM is looking the channel in frequency domain. Okay. So what is the idea in OFDM is that you have a channel you can understand or imagine in your mind that in the frequency. Okay. Here you have a transmitter and here you have the receiver. So transmitter, what is the function of transmitter? Transmitter send the information to the channel. Also the coupling between transmitter and receive the channel is going in frequency domain, you can just think that. Okay. So you have to put data in frequency domain because channel you are imagining in frequency domain. Okay. Then similarly with the receiver, you have to think that the channel output is going to couple with that receiver in the frequency domain, that way you can think. Okay. So input and output, if you are looking here, this is the input and here you are looking the output, that is the frequency domain. So whatever the information you have here in the frequency domain, here you also have information in frequency domain. Okay. But you do the real things in the time. Okay. So you have to convert frequency to time. Okay. So what I am doing here, this information symbols in the frequency domain, then how will convert frequency to time? Inverse Fourier transform. Yeah. So inverse Fourier transform, if you using the discrete Fourier transform, you can use IDFT. Okay, inverse discrete Fourier transform. That generally a tool that is called IFFT, inverse fast Fourier transform, used to implement the DFT efficiently. So IDFT is used here. So this is the frequency symbols. Okay, how many frequency symbols you will put? Here I am just putting n frequency symbols because I am considering n subcarriers. This number of subcarriers I am considering n. So each subcarrier is carrying one symbol. You just think that way. So n symbols I have uploaded here. Okay, then you have a vector. Okay, vector size is n elements in that vector. Okay, so n elements are there. Then what you will do? You can take n size IDFT. Okay, IDFT formula if you remember. So IDFT block is there. Then you have a n symbols in the time domain. So frequency domain symbols are converted into the time domain using the IDFT. Okay, then IDFT matrix I have just written U inverse. Okay, that is just a matrix. Okay. Then you have a then what I am doing, this the time symbols, time domain symbols, then I am adding some cyclic prefix. Okay, CP. So CP is added. CP generally last part of this data symbols in the beginning. So just take few symbols from the last part and just concatenate at the beginning of the symbol. Okay, that is called CP. Then CP is added here. Then we have a channel. Channel you can think that is the output of the channel here, and this the input of the channel. So what is the, if you consider channel is a LTI system, then you can think that is a convolution between input and impulse response of that channel. So channel impulse response I am calling H, input I am just calling the vector D, that is a convolution. I am using the circular convolution. So that's why I am this is the circular convolution, because IDFT and DFT are involved there. Okay, so we have IDFT, if you remember that we have a circular convolution, not the linear convolution. Okay. Then why I am adding this cyclic prefix? Because generally our LTI system has a linear convolution. So convert that linear convolution to the circular convolution. This CP is essential. Okay. So that is the one. Then this is the total n plus l minus 1 symbols I have fed it feed it at the input of the channel, then same number of symbols I am getting in the output. Okay. Then you remove the cyclic prefix, okay, because our only original data is this much, okay, n. So just keep n symbols by removing this earlier part of CP. Then these symbols in the time domain, okay, then time domain, but our original data we are put it in frequency domain. So we have to go back in frequency domain. Then I use the DFT, discrete Fourier transform. Then we have a n symbols in frequency domain. Okay, so then we do the detection here. Okay, so so IDFT, this is a part of transmitter, and CP, this is the part of this one, and then this removing the cyclic prefix and DFT is the part of the receiver. So complexity is split between transmitter and receiver. Only one operation you are doing at transmitter, another one is doing in the receiver side. Okay. Then generally cyclic prefix. After cyclic prefix, what we have? We have a analog to digital. Digital to analog converter. Okay. Then we have a RF front end that convert those baseband signal to passband. Okay. Then we have antenna. Then we transmit the signal. Same thing is this side. Then we do the detection here. So this way you can think the frequency is here, and then frequency is also here. Then we intermediate, we are doing some operations. So this is the OFDM block diagram. So OFDM include basically IDFT and CP at the transmitter side. Then this is the channel. Then receiver side we are doing removing the CP and doing the DFT operation. If you understand 2D format, so what we will do, this is the time and frequency. You put the data symbols in like that. So this is the first red one. You can think maybe pilot symbols are used for channel estimation, because when we detecting the symbols we need channel information. Okay, I am not going too much detail, and that is a mathematical model to compactly represent the output. So what is the output here? You just think circular. This is the channel, this channel, and then this is the data. So this circular convolution I can return using the C. C is a circular matrix that generated using the help of channel. Then circular matrix has a special property. If you remember that first row then second row are related to each other, but by circularly shifting that you can generate the second row. Okay, then circular matrix can be decomposed into the diagonal matrix with the help of DFT. Okay, so that's why there is a DFT. So this the whole operation is related here. Then you are doing the post processing and pre processing. Then you have this diagonal structure here. Then we have seen three, even in fact 4 orthogonal multiple axis schemes. One is the TDMA, another one is the FDMA, third one is the CDMA, and the fourth one is the OFDM. Okay, all are orthogonal multiple axis schemes. So orthogonal multiple axis schemes means at particular resource only one user is present. There is no other users. Okay. Now we are going to know my scheme, non-orthogonal multiple axis scheme. Why we are going to non-orthogonal multiple axis scheme? That idea is that this is not a new concept. This is earlier 80s or 90s people already explored. That is a superposition concept. Okay. So idea is that if you have just one resource, for example, think that, okay, you just think that like you have a power water supply in your house. Okay. So generally what is the diameter of pipe we use? Very small, maybe like even lesser than that. Yeah. Okay. So what if you use the 5-inch diameter pipe, what will happen? Flow is very less, and you are just spending your money in that buying that pipe 5-inch, because we are not going to use full capacity of that pipe 5-inch water tap. Okay. So similar idea here you can think, we have a one resource for particular user. Okay. Let that resource has a higher capacity. Higher capacity meaning is that you can think a good channel. Okay, here we think good channel or bad channel. So let that resource has a better channel or good channel, but our data requirement is very less. For example, that good channel has the capacity to deliver the 1 Mbps data rate, but just our requirement is 1 kbps. So this is the wastage of resource. Okay, we allocated that resource for particular user, but that user's data rate is very less. Okay, so we just underutilizing that capacity of that resource. So that idea people explored in the non-orthogonal multiple access schemes. Okay, so idea is that if you some resources on particular resource we can allocate multiple users. Okay, let one resource is there, 2-3 users can use simultaneously that resource. Okay, so we can enhance the capacity. Okay, so that is the idea. So non-orthogonal multiple access schemes are divided in the few categories. One category is the power domain norma, PD norma. Okay, another one is the code domain norma, and then another one is the hybrid domain norma. Hybrid means a power domain and code domain norma can be used simultaneously. One example is the rate splitting multiple access that may be coming in the 6G. Okay, so PD norma concept is different, because here is the one resource exclusively separately we are looking. Okay, but here what we are doing, we are here code domain norma, we have a multiple resource and multiple users. You can think just a bunch of users, bunch of resource, then we jointly optimizing all the resources. Here what we just doing, we just consider only one resource, then multiple users, then we are utilizing that technique. Okay, so codomain norma, some example is that LDS CDMA, okay, low density spreading. Okay, then LDS OFDM, then sparse code multiple access scheme, and then interleaved division multiple access schemes. Okay. So just I am looking the power domain norma first. So power domain norma, what we doing, this is the orthogonal multiple access scheme. So you see one time of frequency of code, this is x axis, you can think a resource, and y x axis, x axis you can think resource, so y axis you can think power. Okay, so this resource is allocated only user 1, and this resource is allocated to user 2 and 3 and so on. Okay, so this is the orthogonal multiple access schemes, but for example these are the orthogonal multiple access schemes. But here if you look the resource and then power, here one resource is utilized by 3 users, 1, 2, 3. Okay, so 3 users are using the same resource. Here each user is using the separate resources. So this is the orthogonal and this is non-orthogonal. That's why it is called norma. Okay, the users are overlapping. Then question is that here we have a orthogonality condition while decoding the signal. Okay, because this time only one user is present, so interference from other users are 0. But here they are overlapping, so interference from other users are there. So how to decode that user information, individual user information, that is a challenging part here. So what is the challenge we can overcome? By allocating the different amount of power to each user. You can see here this much power is allocated to user 1, this much is this user 2, and this much is user 3. Okay, so ultimately our aim at the receiver to separate out the each user. Okay, because is the all user information are clubbed together. Okay, from that superimposed information we have to separate out individual users information. Okay, so that individual user information can be separated out in norma technique using different power levels. That is the idea in the power domain norma. Okay, so separating out users, we need some extra information. Extra information meaning is that if you have just one equations, you will get here one equations, and how many variables? 3. If each user have x1, x2, x3, so 3 variables are clubbed into just one equation. Y is equal to, let us think, p1 x1 plus p2 x2 plus p3 x3. So one equation, 3 variables we cannot separate out. Okay, so we have to some extra information. Okay, so that extra information we have here, that is a different power level of each user, then we can distinguish them. Okay, so that is people targeting 5G and beyond. It has higher spectral efficiency, as I already pointed out. One resource 3 user can communicate, so we can accommodate more number of users in the system. Okay, that so massive connectivity is also there, higher spectral efficiency is also there, because we can utilize that channel fully. Okay, then but the drawback is a little bit more complex as compared to orthogonal multiple access schemes, because we need something extra here to separate out the users. Okay. So that is the one downlink normal system block diagram. So what I am just thinking here, this is your base station, and then we have 2 users, one is the near user and another one is the far user. Okay, so near user is just think near to the base station, far user little bit far away from the base station. So there is distance from the base station distances are different of each user, near user and far user from the base station. This is the near to base station, that is why I am calling it near user, or so its path loss will be less. Why? Because it is a near, so loss will be lesser. Here this is the far user, so losses will be high. So that is far user or weak user. Okay, when signal transmitted, so you will get less power. So that is why the weak user or far user, here near user or strong user. Okay.
The near user and far user should be aligned.
Aligned means?
If we form a beam forming
Yeah.
in particular direction, so they should be aligned. That's why some near.
Yeah, that is a concept. If you are using just currently we are using MIMO technique, so beam forming is there. So beam is just doing it in each direction, steering the beam. So near and far user should be in the same beam. Okay, then you do the user pairing. So suppose this is the beam, so like far user near user can pair here, then another beam is there, far user near user can separately pair there. Like so, this should be aligned in the MIMO case. Yeah. So the near user and far users are there. So let near user channel I am saying H1, okay, and then far user channel I am saying H2. Okay. So condition is that H1 is square. How to calculate the gain or power? You have a signal, then take the absolute value, then you square it. That is generally called, then average it out. That is generally called power or energy. Okay. So here I am just calling that gain. So gain, what I am doing, H1 take the absolute value, because the channel is a complex quantity. Take the absolute value, square it. So that is the channel gain. Similarly here you take the absolute value, square it, channel gain. So channel gain of this user is higher than this user. Okay. Then what I will allocate P1 power to the near user and P2 power to the far user. Okay. This is the weak user and this is the strong user. Okay. So communication, when you transmitting the data, what is our requirement? You just transmit power that so that user can decode its information successfully. That's it. Okay. There is no need to allocate extra power. If it can decodes signal at 5 dB, SNR like for 10 dB for example, there is no need to transmit 15 dB. Otherwise, what will happen? Your battery life is going to reduce. So there is no need. Generally, 10 dB is sufficient. Okay. So so we allocate less power to the near user because the losses are lower. We allocate more power to the far user. That is the idea in the downlink normal system. Then what we will do? Far user received signal is expressed as this one H2, that is a channel. Then is a superimposed signal, that is a P1 X1. This is a superimposed signal. So then P1 X1, H2, P2 X2. Then you can see this P2 is higher than the P1. Okay, H2 here is common, H2 is also common. So this quantity is higher than this quantity, isn't it? Okay. So by considering this quantity as an interference, we can decode the signal X2. Okay. So far user are able to decode the its own information while considering this user as a interference, or this quantity as a interference. Okay. So this way we can decode the far user information. So what is the condition? Condition is that you allocate P1 and P2 suitably so that we can decode this user information. Okay. Similarly, you can see here this near user H1 is there, then this one there. So you can see P1 is smaller, P2 is higher. So this quantity is higher, this quantity is lesser. So near user cannot decode its own information. You can think interference level is this much, signal desired signal power level is this much. So you cannot decode. So what is the first thing? First remove this thing, then we will get this thing. Okay. So so what is that? This is already higher, so let decode it first. Okay. After decoding, what we will do? We will just remove it here. Okay. So first you can think interference level we have find out and remove that interference. Then we have only signal. Then we decode the near user information. That is the idea. So this is called SIC, successive interference cancellation approach at the near user. So downlink strong user or near user applies SIC based signal detection. SIC signal based detection means it first removes interference label. Like interference means other user information, weak users. Okay. So near user first remove the weak users information, then decodes its own information. Okay.
Sir, it will not create a problem of security because we are.
Yeah, that is a main drawback in the power domain norma. So that's why this 5G 3GPP haven't considered this one till now. okay, but they are thinking 5.5, okay, or some modified version of this one, okay. That is security is the issue, but security is not mainly the issue. Why it is not mainly the issue? Because this is just we are getting the bits, not exact packet, so that is not physical, that is a higher level, that is not much problem. But problem is that how much gain we are getting, okay, like OMA and NOMA. If you are just getting a very less gain, then there is no need to implement. If you have a significant gain, then we will go. So people in different environment are still exploring this thing, okay. So this is the SIC based signal detection. So SIC generally remove the weak far user information before decoding the near user information. So this extra block is coming. So this is adding little bit extra complexity at the receiver side. So yeah, this I already pointed out here. Then this is the mathematical expressions. So this is the composite signal. Then you do this one SIC. So here I have just plotted the performance of near user and far user, okay. So what I am considering here, first case I am allocating the power. Power is I am considering total power is 1 unit or 1 watt. Then P1 is equal to alpha 1 P. So that means P1 is equal to 0.1 and P2 is equal to 0.9 unit. Okay. Here P1 is 0.3 unit, P2 is equal to 0.7 unit. That is the meaning. Okay. P1 is equal to alpha 1 P. P is the total power. I think maybe I can write here this P1 is equal to alpha P. So that is alpha is 0.1. So it is a 0.1. P is equal to 1. That is a 0.1. Similarly, P2 is equal to 0.9. So that is the 1. So total power I am just keeping constant 1 unit. Then similarly you can do in the second case. Okay. Then I pointed out channel gain difference is this much, 32 times higher than the H1. Okay. Then I am just generating the results, and the x-axis is the SNR and dB, and this is the bit error rate. And I think I am using the BPSK scheme for both user, near user and far user. Okay. So you can see that after SIC, perfect SIC, if we have Y1 is perfect SIC, meaning is that I am talking about here this point. This is Y1 tilde after removing the far user interference. So H1, P1, X1 plus N1. So you can see after SIC there is no interference from the far user. Only one user information is present. One equation, one unknown, Y1 and X1. From the Y1 tilde we have to decode X1 only. So there is no interference. So after SIC this user will get full diversity because interference is not there. Then far user or second user, that is a weak user, this term is still present. Okay. So this is the interference you can think. So we have to decode X2 from the Y2 by considering this quantity as an interference. So interference will reduce the diversity of far user little bit. Okay. So that's why I
Interference and noise become non-Gaussian in nature.
no, it's a Gaussian noise I am just considering.
No, but interference is not Gaussian.
Yeah, interference non-Gaussian. Yeah. So I am just considering
Both is non-Gaussian.
non-Gaussian. So I am just considering this one is just interference and to tilde you can think. So you can see that this U1 and U2 solid line in this case alpha 1.1 and 0.9. So you can see U1 performance, near user performance is better than far user. Why it is better? Because you can see there is no interference. As SNR increase, performance improve. Okay. But if you can see that case, this one far user case, interference is present there. So it will saturate out. If you just go even beyond 30, you will see it will saturate. Why it will saturate? SNR is increasing. So this term is going to 0, but this term is not going to 0. This is always present. So far user will decode its information in presence of interference. So after certain SNR, it is going to saturate. So their error flow range exists. Okay. Then you can see if you change this power allocation, then level is going to change. You can see 0.3. So near user performance is improving, but far user performance is going to degrade. Why it is degrading? Because this quantity is going to more. Okay. Because earlier case it is 0.1, now it is 0.3. So that case performance is going to degrade. Okay. So this is some code. Then this the SIC in uplink scenario. So uplink scenario meaning is one near user and far user. You can think both users sending the data to the base station. Then base station is applying the SIC. Then so SIC means one user information decoded here, another user information decoded after that. Okay. Then this downlink scenario, we just are looking the sum rate capacity of both users. So as I pointed out, downlink broadcast channel single user bounds as this one R1 is equal to less than log 1 plus p h1 square n naught. What is that meaning? Just think that I am considering that only 1 hertz bandwidth is available, so b term is not coming. Total power is p, okay. H1 is the channel gain square, and naught is the noise PST. Okay, so this you think you as SNR. So only one user is present, then one user is present means whole power is allocated to the single user. So second user is not present. Basically this one is there. P1 plus P2 is equal to P. So if P1 is equal to P, that means P2 have to be 0. So only one user is present. So that is the bound. Okay, that is if one user is present, then R1 has to be less than this quantity. Similarly, if P1 is absent, only P2 is present, whole power is allocated to the second user, so R2 is less than this quantity. Okay. Then let both are present, then P1 and P2 power allocated, so they are this one. R1 is this one, P1 H1 is square upon N naught. Why this one? There is no interference, as you pointed out. Here there is no interference because using the SIC we have removed the far user information. So that's why this rate, and then R2 you can think it is considering near user as a interference. So interference term is also there in the sum capacity formula. Okay. Then this R2 can be written in this way. Then we can maximize this sum rate region R1 and R2. So how to maximize sum rate? Only depending on this P1 and P2 if H1 and H2 are given. Okay. So this is just a plot which sum rate of user 1 and sum rate of user 2. So you can see that these are the corner points. Corner points means x axis y is equal to 0. So only one user is present. So corner point you have log 2 1 plus p h1 square and not. At this corner point x another user is absent. So only one user is present. So the second user p h2 square upon n naught. So these are the corner points. So at the corner point, what is which multiple axis scheme we are using? Orthogonal multiple axis scheme. Only one user is present. So this corner represent orthogonal scheme OMA. Okay, but NOMA, this line is also in the OMA. This black line. Why in the NOMA? OMA? Because suppose you have a frequency 1 hertz, and if you want to communicate or divide the 1 hertz into the 2 users, what you will do? We can do maybe 0.5 to one user and 0.5 to another user, or maybe 0.2 to one user and 0.8 to another user. So this line you can have to follow. Okay, that resource f1 plus f2 is equal to 1. Okay, so OMA user will lie on this black line. Okay, then this red line here denoting the NOMA. Okay, so this gap is there, black line and red line. Why? If you look the capacity in the black line, you have this much capacity x axis and y axis. For example, at this point, okay, user 1 data rate, user 2 data rate. But if you have a NOMA, you can go up to here. So this is the user 1 data rate, user 2 data rate. For example, if you just lying in this one, user R1 data rate you have increased and keeping the same data rate of user 2. So total capacity is going to, system capacity is going to increase. Okay. So this triangle generally called for OMA. Then how much gap is there? Maybe red line is here or maybe here. That depend on the channel gain difference between two users, that we will see. Okay. Then uplink scenario, we have again quantify these corner points. So uplink scenario is there, you have a base station, then multiple users are sending data. So you can think user 1 has a power P1, user 2 has power P2, then this is the point, corner point, only one user is there, another user is there. Another case what will happen, both users are transmitting to the base station, then maybe both users power is just added together. Okay, so total power is going to increase. That way, sum rate you can bound by this. Okay. So that's the case. Then I will just plot it here, down uplink scenario. So here this is the corner point, as I pointed out, corner point. So what is the corner point? This is the user 1, its power is P1, so corner point is this one. Its power is P2, so corner point is this one. No other user is present. Okay. Then this OMA scheme is represented on this line, black line. Then you have another point if you are using the NOMA scheme. So what that point A? Point A, if you look, this is the sum rate of user 1 and this is the sum rate of user 2. Okay. So what is that meaning? At point A both users are present. Okay. This is just applying the SIC free scenario, sorry, interference free scenario sum rate. At this point user R2 is considering that user 1 is also present. Okay. So user 1 is present, so it creating the interference, then we are calculating the capacity. So at this point what we are doing? We have a received signal, let example Y, then we will decode second user, then we will decode first user. Okay. So you can see, say, while decoding the second user both users are present, that is why this interference is coming here. Okay. After second user we have decoded, we have to remove its contribution from the received signal using the SIC. Then what will happen? Second user is not present, only one user is present, so that is the first user. So this much there is no interference here. Okay. Similarly, so here we are doing the reverse. What is the reverse? Both users are present. So at this point you can see this is the user 2 data rate and this is the user 1 data rate. So at this point what we do? We receive signal Y, then first user we are decoding first. Okay. Then we are decoding second user information. Okay. So first user we are decoding, so second user will be treated as a interference. So that's why interference is coming here. And then we are decoding second user, so that is a interference free. So that is a pentagon is formed. Okay. Generally, if you have a k users, then you have a k corner points. Then this is the one example. Okay. So this example I just included from that wireless fundamentals from the David TC book. Okay. So this is the SNR1 20 dB and the SNR2 0 dB. 0 dB means weak user. This is a strong user. Okay. Total power is 1 unit. Then SNR we calculated H1 is square n naught and H2 square n naught. Then OMA scheme we are using time division duplexing, means half time slot is allocated to user 1, half time slot is allocated to user 2. So that's why 1 by 2 in front is coming. Okay. Then this is the sum rate of user 1, 1 by 2 log 1 plus H1 square. So you can put this the data rates. R2 is equal to 1 by 2 log this one. So this is the data rate of user 2. So if you have this SNR and if you are using the OMA scheme, you have the sum rate 3.3 and 0.5 for first and second user respectively. So this is the big user, so obviously its data rate is lower. Okay. Then if you are using the NOMA technique and power splitting factor, I am just considering 0.2 and 0.8. So that total power is equal to 1 unit. Okay. Here I am just considering P is equal to 1 because whole power is utilized by individual users. Okay. But users are differentiated using the time slot, that is why 1 by 2 is coming in front. Okay. Then you have R2, so that this the interference scenario. So if you put all the values, you will get this one is the big user sum rate, because big user detect the signal in interference scenario. Then this is the first user, or this is the strongest user, so sum rate is coming 0.439. So you can see in NOMA scheme, this NOMA scheme, weak user in capacity is also increased from 0.5 to 0.7 and strong user is also increased from 3.3 to 4.39. Okay. So that is the advantage of NOMA. Then corner point you can also calculate. Corner point means allocate whole power to the single users, then is 1 and I think 6.68. Okay. So I just plot it here. Yeah, so that is the one example, numerical example I have considered. Then you just go to this optimization. So in OMA scheme we can also optimize. What we can optimize, as I putting 1/2 half. This 1/2 we can also utilize, maybe 0.2, 0.8, 0.3, 0.7 like that. Then power we can also utilize. Okay. So I am not going to details here. Then I have just plotted some rate user 1 and user 2, and this is the norma scheme I am using, okay, according to these channel conditions, SNR 0 dB and 20 dB. So if you can see the norma, and then the red line is representing the OMA. Then OMA I have also optimized for this scenario, so this little bit higher. So you can see that gap is there. Okay, so if you are in this line, you can have better sum rate as compared to this point. Then further I have increased the gap between user 1 and user 2. So you can see 30 dB gap is now. Earlier I have considered only 20 dB gap between the SNRs. So here gap is 30 dB. You can see performance is further improved. Norma can give higher data rate. Okay. Then third case I am considering that gap is very low. Almost both are similar. User 1 and user 2 are locating at the same distance from the base station. So gap is almost very similar. So you can see 0 dB and 1 dB. Then the gap, that improvement is going to reduce. There is no improvement, if you can see, almost same. Okay. So conclusion here is that OMA is more useful when you have the users have the same distance from the base station. That time we can use the OMA. If you have the gap, particular threshold you can decide, that time we can use the norma and enhance the system performance.
So these results are considering a downlink side or
Downlink.
Sir, but incorporating the norma in downlink side is difficult because signal processing is done at the tiny mobile handset. So
No, nothing is more like complex here. As I pointed out, only one extra block is setting this SIC. This user know extra thing. Okay. Only thing is one extra is here. He is just decoding twice. So that meaning is that channel H1 is required. Either doesn't matter whether we are using decoding the single user or multiple user. So H1 is required. So if SIC is not there, even in OMA scheme we also need channel information. So channel information we are not doing multiple times, just only as usual. Okay, so that's why complexity is not going to increase. Only this extra block is included, so a little bit like addition and multiplication will increase. So this is the code. Then here I have considered the impact of SIC, when SIC, successive interference cancellation, is perfect or not. Okay, perfect means far user information is perfectly decoded and then subtracted. Okay, otherwise what will happen if far user information is not perfectly decoded, while you applying the SIC, some residuals are present. Okay, so some contribution from the far user is still present after SIC, that is called imperfect SIC. So I have modeled that factor like this one. So if eta is equal to 0, that means perfect SIC, because this part is going to 0. If eta is not 0, then some residuals are present. Okay, so that time I plotted this scenario. I plotted noise PSD I have considered minus 173 dBm, and then bandwidth I have considered 1 megahertz, and then path loss factor I have considered 4, and that distance is this much, or power allocation is this much. Okay, so
imperfectness come into picture due to the unavailability of CSI of our user at the
basically what will happen if you estimating the channel. So at low SNR you can think some definitely channel information is not perfect. Yeah, but high SNR generally that is not visible. Why not visible? Channel we consider the quantization labels. So if you little bit here and there, we can manage at particular quantization level. Then noise is also very low. So high SNR scenario, that imperfect SIC practically if you implement it is not visible, but low SNR it is visible. Yeah. So this is the case. Well, so I am just total sum rate I am plotting R1 plus R2. Okay, so sorry, R1 I am just plotting, user 1 information I am just plotting this case. So you can see this eta is equal to 0, so this interference is not there. So if SNR increases, sum rate continuously increasing. Okay. Then you can see if eta is not 0, so interference is there. Okay. So SNR is increasing, so noise is maybe going 0, but this term is fixed there. So this term start dominating. So you can see sum rate is start saturating, here saturating, it's saturating, then here it starts saturating maybe after this point, but here maybe started saturating this point, here already started after this point. Okay. So that is the case of imperfect SIC. So if you have imperfect SIC, near user sum rate is also going to saturate. Okay. Far user information sum rate is already saturated due to the interference. Okay. Then here I have just plotted the impact of number of users on the sum rate. Its meaning is that what is the number of users? Here I have considered only 2 users. Earlier cases, user 1 and user 2, near user and far user, 1 resource and 2 user. Okay, someone can let I have 3 users on the 1 resource, I can allocate 3 users. Okay, then another can let I allocate 10 users on 1 resource. Okay, so what is the limit? How many users we can allocate? Okay, apart from the hardware complexity, we can increase multiple users. Then what will happen? If you can see that sum rate versus number of users, sum rate initially start increasing as number of users increase. This is the transmitted power. Okay, noise PSD is fixed as earlier slide, minus 173 dBm. Then you can see that earlier starting as number of users increase, sum rate increase, but after certain point sum rate start decreasing. Okay, that is the why it is happening, due to the interference. Okay, multiple users are there, so allocating the power according to these conditions, it is also challenging. So interference is dominating, that's why sum rate is going to decrease. So after certain number of users, you cannot allocate the users. So this cooperative norma maybe you already know what I am doing in the cooperative norma. Basic idea is cooperative norma is there. If you just see this slide, yeah, this slide for example, here what is this? This user is decoding both user information, near user and far user. Okay. So cooperative norma, what we will do in the second phase, we divide the total time into the slots. Okay. So second slot, what this user will do, this already decoded this user information, so it also try to send the information to this user. So this user is getting information from the base station directly in the first time slot, and then second time slot this user also getting information from this user. So it getting 2 time information, from one time from directly base station, another time from the this first user. So it has 2 link, so it has 2 diversity. Okay, if you just ideally think that. Okay. Yeah, time diversity obviously. Okay. So that's why this user performance is going to improve, because due to the diversity scheme. Okay, that is generally I am referring here is the cooperative norma. So this user is helping to this user, that's why it is called cooperating. Okay, this is cooperative user in this system. So that's the performance of cooperative. So you can see cooperative, this performance improves. Then this is the code. Then I am moving to the code division multiple access scheme. Okay. So code division multiple access scheme, just think in terms of the CDMA system. Okay, code division multiple access.
CDMA technology is not used after third generation.
Yeah.
There's some issue with this technology.
Oh, issue is that CDMA, as I pointed out, looks the channel in time domain. So what the problem is coming, that is the equalizer in the doubly dispersive channel. Okay, because currently we are moving higher data rate. So higher data rate means the time slot is going to reduce. So that interference level ISI, one block to another block, is severe as compared to previous generations. So when ISI is severe, then we need more complex equalizer. Okay, so that is the one difficulty. Another difficulty in the CDMA is that more number of users are coming, because earlier less number of users. So more number of users are coming, then some rate is going to saturate, because you have a floor and then over the floor you are spreading the users. So one user layer, second user layer, as you have multiple users, so layers are more, so your interference level is very high when you just one user looking the interference from the other users. For example, 100 users are there in the system, so first user looking the interference from remaining 99 users. Okay, so that interference issue is also there, so that CDMA cannot come back. Okay, that is one issue. Another so massive connectivity point of view is issue. And then another one is that if you utilize CDMA fully, that we use the rack receiver, if you remember the comb receiver we call. So that channel information is accurate is required. So rack receivers, that's a channel complexity. If you have multiple racks, so that channel estimation part is more complex. So that's why people look in this OFDM, frequency domain channel. So what they do, they divide the frequency smaller bands, so that time slot is increased. A smaller frequency means higher time duration. So that way they combat ISI. Yeah. So this CDMA block I am just using to help out this code division multiple access schemes. Okay. So CDMA basically what we do, we have a multiple users, user 1 up to user k users are there. So first what we will do, we have a information bits, then this going to multiplied by the code. These are the code S1, S2 I am referring code, then these are the waveforms, then physical waveforms you can think. Okay, then they are added over together, then transmitted, and then receiver side what I am doing, user 1 is this branch, so user 1 use this code S1, S1 is multiplied, then we have a correlator, then we have a COM detector. Okay. So this S1 is orthogonal to S2 and S3, so on, orthogonal codes we are using. So this contribution of this one S2 and S3 here is going to 0. Why is going to 0? Because S1 is orthogonal to remaining codes. Okay. So here this one is doing the spreading, basically you can think this is the spreading sequence. Spreading sequence meaning is that if you have a 10 resource for example, okay, so what do? I do the modulation. After modulation means information bits are mapped to the symbols, constellation points. Constellation points, if you remember that QPSK for example, we have these 4 constellation points. This is the real part and this is imaginary part. So you doing the modulation, so information bits B is mapped to the symbols X, maybe this is X, X can take these 4 values. Okay, I am just not writing. Then after the constellation mapping modulation, what we will do, I spread this in symbol over multiple resource. For example, this is my one frequency, another frequency, third, and so 1, 2, 3, 4, maybe or 5. Okay. Then I will spread my information X over these 5 resources. Okay. Then similarly, this user will take its information, map the constellation points. Then using the S2, I will spread that user symbol over these 5 resources, and so on. Okay, that is called spreading. Okay. So that is the spreading is happened due to S1. So size of S1 define how many resources we are using for spreading in the CDMA system. Okay. Then de-spreading will happens here. Then we have a detector. So multiple resources and multiple users are there, you can think, okay, in the CDMA system. Then receive signal particular chip or particular resource we are calling nth resource or nth chip is written as this one. K number of users are superimposed, you can think here. Okay. And this SKN is representing the kth user spreading sequence on the nth chip. Okay. So this, so you can see this SK here, that is the spreading sequence, have multiple chips, NC resource or chips we are saying. Okay. Then you can see that this factor graph meaning is that this is the number of users, these are the chips. So you can see user 1 is spreading over this first chip and that 5th chip. Similarly, user 2 is spreading over this chip and this chip. Okay. So this is called degree of resource is 2. Why it is called? Each user have 2 chips while transmitting the data. Okay. And this is called degree of chip or degree of resource. Degree of resource is 3. Its meaning is that particular resource is carrying the data of 3 users. That is the meaning. And this representation generally called factor graph. Okay, factor graph. And this factor graph can also be written in terms of matrix using the number of rows and columns. So rows representing here that number of resources, and that columns are representing number of users. Okay. Then if you consider the LDS OFDM, so what is that? This is the mapper, that is a spreading, then this is the OFDM modulator, then is the waveform, then you just transmit. Okay. So this is the spreading block, spreading. Okay. So here two things are happening different time instant. This is the modulation, then spreading. Okay, 2 steps process: modulation, then spreading. So what I am doing in the sparse code multiple access scheme SCMA, unlike this CDMA or LDS system, here modulation and spreading in the 2 steps. In SCMA we are doing in the single step. Okay. So single step, by doing these 2 process in the single step, we can enhance the system performance. Okay. System performance enhanced due to this shaping gain. Okay. Shaping gain meaning is that suppose you have some fixed boundary. Okay. Then within the boundary you are arranging the points. Okay. Shape of the boundary you can manipulate, so that you can get some gain at the receiver side in SNR gain. Okay. That is generally we call shaping gain. So SCMA, what is the user data directly transmitted to the transmitted sequence. There is modulation and spreading happens together. Okay. So modulation and spreading happens together, that generally we use the code books. Okay. So here you can see I have 6 users, they represented 1 to 6 users. Then this 4 resources, this rows are representing first resource, second resource, third and fourth. Okay. So 4 resources, 6 users. So number of resources are less than number of users. So this is the non-orthogonal multiple access schemes. We cannot orthogonally allocate resources to the users. Okay. Then you can see this is the user 1 code book. Okay. Then each code book has 4 columns. 4 columns means 2 bits per symbol. Okay, 2 bits information symbol. So that's why this is the 2 bit symbol, means we have this combination like 0 0 0 1 1 0 1 1 for example. Okay. So let user 1 has information 0 0, we will pick this column. If user has information like 0 1, then we will pick second column and so on. Okay. So 4 different symbols, then we need 4 different columns, and this is called code book. This is called code book of user 1. This is the code book of user 2. So each user have 2 bits per symbols. Okay, that's why I am using 4 columns in each code book. If they have different, you can use the different number of columns. So information here is 0 1, then we can select second column. Here information is 1 0, so we can select third column. Then here we have a information is 0 0, so we can select first column and so on. So 6 users, we have selected 6 column. This column selected based on each user data. Okay. Then these different, if you have a downlink scenario, then what will happen? These code books are superimposed, they are added together. So we have to add, then we have one superimposed code book. Okay. So then we transmit this superimposed code book, code word. Okay, this is the code book, and what particular code column we are calling code word. Okay, so this superimposed code word is transmitted, and the receiver side, from this superimposed code words we have to separate out each user data. That is our target. Okay, so these code books are priorly designed. Priorly designed means before transmitting the data information of each user, you have to design the code books and store at the transmitter and receiver side simultaneously. Okay. So how to design the code books, that is a different issue, that depend on the number of users, depending on the number of resources, depending on the modulation order. Okay. So that is I am not going into the details, but these code books generally depend on these factors. Okay. Hetamart code is like just -1 +1 we can use that, yeah, but that way we will not get the performance improvement.
And PM code, pseudo random code.
Pseudo random code, yeah, that we can also use, but if you just look, maybe I have shown the performance, that performance is still not like optimal. Okay, that is like LDS, low density splitting code. So that is the overall motivation in the SCMA scheme. So SCMA schemes, what is the main idea? We have to consider multiple users, multiple resources simultaneously, then optimize the system performance. That is the whole idea. Okay, so this is the system block diagram in the downlink scenario. For example, 6J users, then each user map their bit information to the code words, then these code words are superimposed, then transmitted, then this is the channel, then user 1, user 2 up to user j. Here channel you can see this is a vector, not a single quantity. Why it is not vector? Because here k number of resources we are using, so this is a k dimensional vector. So I have just written here diagonal h1 j1 hj. Okay. So this xj, for example, maybe then SCMA can be understand through the factor graphs. Factor graph, as I already pointed out, it has number of users, number of resources. So users, like 6 users and 4 resources, then you can see user 1 carrying information of first, second and third user. So it's the degree of a resource node is 3 and degree of user node is 2, and this is the factor graph. Factor graph can be written in terms of matrix. So the number of columns denoting the number of users and number of rows denoting the number of resources. So you can see this factor graph is a sparse, some zeros are there. Okay. So sparse means only few non-zero entries, that meaning is that called sparse matrix. Then this factor graph is sparse, so we can use message passing algorithm. Okay, message passing algorithm generally used in the LDPC decoding scheme. So I'm not going to details. So I'm just summarizing this normal scheme here. So SCMA performance will depend on this, how many number of users are there. Overloading factor is there. Overloading factor means ratio of number of users divided by number of resource. Okay. Then modulation order is there. How many columns are there in the code word? How many bits per symbol we are transmitting? That is also depend. What happen? Okay. Then codebook design, that is a challenging. Performance of SCMA will depend on the codebook design. Okay. If you don't have proper codebooks, then you will not get any improvement in the system design. Okay. Then complexity, receiver side we are using message passing algorithm. So its complexity is like MDF. M is the order of modulation and DF is the degree of resource node. Okay. So its meaning is that if you are using a more number of bits per symbol, that means complexity is going to increase, or if you are using more number of users, so that way performance, if more number of users, then DF will increase, that complexity will increase. So we need some simple algorithms to decode the signal. Then power allocation among the users is also crucial. Okay. Then SCMA we can explore with massive MIMO system design. Okay. Here we considering the number of users and number of resources to design the code books. If massive MIMO system is there, then number of antennas we can also consider in the code book design. Okay. Then, so if you have any question related to NORMA scheme, non-orthogonal multi scheme, you can ask. If no questions, then I am just briefly introduce. Yeah. exit then थोड़ा गड़बड़ है, इसको आप एग्जिट कर दीजिए फिर से, जस्ट 10 minutes more. So I'm just going only IRS, intelligent reflecting surface. So intelligent reflecting surface, what we are doing, we have a source and we have a destination. As I earlier pointed out, that wireless channel depend on the surroundings. Okay, it is not in our hand. But if surroundings, buildings, we can do some kind of polishing or we can install some kind of material. Okay, infrastructure is there. Okay, so that is calling the IRS, intelligent reflecting surface. So if we just install the IRS in the buildings, in the communication scenarios, then the channel we can manipulate. Okay, then people will say, oh, if you installing the IRS, then cost will be very high. Okay, but this IRS is very simple device. Okay, you can easily easily install in the buildings and low power consumption device. Okay, like a relay we use. A relay generally is a power consuming device, generally a transceivers relay. Okay, this generally passive in nature. Okay, only few element you can made active to control the IRS or estimate the channel kind of thing. This is not exactly metallic. This is fabricated using that material. Okay, that meta materials. Yeah. So I'm just this green color. I'm just representing this just one element. So you have a multiple independent elements. So that's why I'm using the gap. Okay. So you have n number of independent elements at this plate. You can think that. Okay. Each element independently tuning the received signal phase. Okay. Then by tuning the phase, so what that this is the incoming signal at, for example, this element, then this element will tune the phase of this incoming signal. Which direction it will tune? That towards the destination. So it tune the phase towards the destination, and similarly this element will also receive the signal from transmitter and it will tune the phase towards this destination. Okay. Yeah, generally I have some material. I am not aware of that. So that a pin diode, all these things people use meta materials. Okay, so that by changing the biasing, all these things we can tune the phase. Okay. Yeah. So so every element will focus the reflected signal towards this destination. Then destination will, what will happen if all the signals are coming in the same phase? Then what will happen? They are added together coherently. Maximum ratio combining will take place. Okay. Instead of doing the maximum ratio combining here using a multiple antenna, but not so that we are doing the maximum ratio combining basically here using the IRS. Okay, that is the main idea, nothing new concept. Okay. Yeah, G1 information and H1 information is required at IRS. Why? So that's the feedback controller is there. Okay, that can feed the information to the IRS. Okay. So practically it is very challenging to get the perfect phase information, but if you just quantize the channel in 1 bit or 2 bit, we can do it. Okay. So the basic idea is that this is the channel from source to IRS. Okay. Source to IRS, then this is the IRS to destination GN. So nth element I written this way. Then this is the IRS response AN e ki power j theta n. So IRS element what is doing? Phase shifting it is doing, and then reflection coefficient is also associated. That is generally less than or equal to 1. Okay. Then if you cascade the link, then cascaded link is written this one, product of this link, then IRS response, then this reflected link. So 3 together are written, then we can mathematically write this one. Then maximum value of this quantity, when we can get the maximum quantity when phase is equal to 0. Okay. So phase is, if this is the real quantity, then is a phase should be 0. Then phase 0 can be theta n is equal to minus of this one. Okay. So that is called co-phasing or optimal phase setting at IRS. Then effective all IRS yeah, the nth element at the IRS. Yeah. So there is a summation over n, then Hn Gn, then perfect phase cancelled, then this phase will go out, then you have this one G1 matrix form, it can be written as this one. Okay. So, you can see that by using a large number of elements we can increase this factor. Okay.
We are using m number of IRS
Yeah,
elements.
yeah.
So can we add a summation, one more summation here to the equation?
Oh, yeah, that is a possible if you can use the MIRS, signal is coming from MIRS, but that we have to look that perfectly possible or not. That here. What will happen, because that is a little bit more challenging. Why it is more challenging? Because this is the one link here. Okay. If you have another IRS, then we have another link. Okay. So like then this another link is there, multiple IRS there. So multiple links are there, and the which one link phase we have to consider, because at a time IRS can take only one value. Okay. So so according to which link we have to set, that we have to optimize it. So that is a block diagram. You can think IRS can be put, then communication is happening with the help of IRS. Okay, so I'm just stopping here. So you can see SNR gain we can achieve with the help of IRS element. This is a number of IRS element. So as element are increasing, SNR gain is improving at the receiver. Okay. So I'm just summarizing here that as IRS element, if you have a large number of IRS element, we can enhance the SNR at the receiver side. Okay. So that is a take home message using the IRS system design. So I'm just stopping here. Yeah. So I'm not going too much detail. Yeah. So this is my collaborator. Yeah. Thanks.